Picture yourself standing at the edge of a massive cliff, staring out across a canyon so enormous you can't even see the far side. You know something extraordinary is over there. Maybe another world, maybe proof you are not alone in this universe. But there is no bridge, no rope, no path, only air, silence, and an impossible gap between you and the other side. That is exactly where humanity stands today, staring across the cosmic void at our closest neighboring star. Proxima Centauri is just 4.24 light-years away. By galactic standards, it is practically our next-door neighbor. And yet, with every rocket launched, every probe hurled through space, we still cannot reach it, not even close. This is not about needing a bigger engine. This is a confrontation with the fundamental rules of our universe. In this video, we will break down exactly why the nearest star remains completely beyond our reach. Let's start with something familiar. The Moon sits about 384,000 kilometers away. Light crosses that distance in just 1.3 seconds. Apollo astronauts covered that same distance in roughly 3 days. That feels manageable. That is a human-sized journey. Now consider the Sun, 150 million kilometers away.
Light takes over 8 minutes to reach us from our own star. If our Sun vanished this very second, you would not even know about it for more than 8 full minutes. But those distances are absolutely nothing compared to what waits beyond the edge of our solar system. Proxima Centauri sits approximately 40 trillion kilometers from Earth. 40 trillion kilometers. Your brain skipped over that number. So let us make it real with a scale model you can actually picture. Shrink the Earth down to the size of a marble and set it on a table. The Sun would be about 30 meters away. On that exact same scale, Proxima Centauri would be 8,000 kilometers from your table. That is New York to Tokyo. A marble, a 30-meter sun, and then 8,000 kilometers of absolute nothingness before you reach the next star. So how fast can we actually travel? The quickest object humanity has ever built is the Parker Solar Probe. At its absolute peak, the Parker Solar Probe blazes through space at around 700,000 kilometers per hour, fast enough to travel from London to Sydney in under 2 minutes. It sounds extraordinary. It is still nowhere near enough. At that record-breaking speed, reaching Proxima Centauri would still take over 6,000 years. For context, 6,000 years ago, humans were just inventing writing. The pyramids had not even been built yet. If the Sumerians had launched a probe at Parker speeds on that very day, it would still not have arrived yet. And Parker only hits those speeds by falling toward the sun, borrowing energy from our star's own gravity. A ship heading outward toward another star would be fighting gravity the whole way. It would be far slower. Voyager 1 has been flying since 1977 and just crossed out of our solar system. It moves at 61,000 kilometers per hour. At Voyager's speed, the journey to Proxima Centauri would take over 73,000 years, and it is not even pointed that direction. You might be thinking, just build a bigger rocket, carry more fuel, push harder. Sounds logical. It is actually a trap. There is a formula in aerospace called the Tsiolkovsky rocket equation, and it is completely unforgiving. Go faster, you need more fuel. But fuel has mass. That mass needs more fuel, which adds more mass, which needs more fuel. To push even a modest spacecraft to just 10% of light speed using chemical rockets, you would need more fuel than exists on Earth. This is not about building a bigger tank. The fuel requirement is so extreme it breaks the entire concept of rocketry. The rocket equation is a wall. Chemical propulsion runs straight into it. No amount of funding changes this physics. But chemical rockets are not the only option. Scientists have been designing alternatives for decades, and some are genuinely clever. Ion thrusters ionize a gas, like xenon, then accelerate charged particles with electric fields. The thrust is nearly weightless. The push is barely enough to move a sheet of paper, but it runs continuously for months, and the speed builds slowly. Then there is nuclear thermal propulsion. A reactor superheats hydrogen, which blasts out the nozzle at double the efficiency of chemicals. And even wilder ideas, nuclear pulse propulsion, where a spacecraft literally rides the shockwaves of nuclear explosions behind it. Project Orion explored this in the 1960s. On paper, it could reach a few percent of light speed. It never left the drawing board. Here is the deeper problem. Even the most extreme of these systems only gets us to a few percent of the speed of light. At 5% of light speed, the trip to Proxima Centauri still takes approximately 85 years, a full human lifetime. At 10%, you cut it to about 43 years. Better, certainly, still an entire generation of someone's life spent in a metal tube. And none of these propulsion systems currently exist in any form that could carry human beings. These are blueprints, not spaceships. Now, here is where it becomes truly sobering. Even if we somehow built a ship that could go much faster, there is still a wall. Nothing with mass can travel at the speed of light. This is not an engineering challenge. It is a law of the universe. Einstein's special relativity shows that as any object with mass approaches light speed, the energy needed approaches infinity. Not a very large number. Infinity. You could harness a whole star's output, and it would never be enough. This means interstellar travel will always be slow, even in the most optimistic scenarios, with technologies not yet invented. The universe is simply too vast, and its speed limit too absolute. Decades minimum. That is the ceiling, not the floor. Let us take stock of what we face. And even if we solved the propulsion problem entirely, the journey itself would try to kill the crew. The moment you leave Earth's magnetic field, you enter an invisible shooting gallery of high-energy cosmic rays. These particles are accelerated by supernovae and other violent cosmic events, and they bombard everything in interstellar space. On Earth, our atmosphere and magnetic field block over 99% of this radiation. In deep space, there is nothing to protect you. On the International Space Station, just 400 kilometers up, astronauts receive 50 times the annual radiation dose of people on the ground. And shielding is not a simple fix. Thick walls of lead or water block some rays, but dense materials create secondary radiation. You try to block the bullet, and the shield itself creates shrapnel. The solution becomes part of the problem. Over a journey measured in decades, the crew's cumulative radiation exposure would cause devastating, irreversible biological damage. Radiation is invisible, silent, but there is another threat the crew would feel every single day: the absence of gravity. Without gravity constantly pulling on your skeleton and muscles, your body begins to quietly consume itself. Bones lose 1 to 2% of their density every single month. Muscles waste away, even with 2 hours of daily exercise. Some ISS astronauts, after 6 months in space, never fully recover their original bone density. Now stretch that to 40 years. The human skeleton would become so fragile that simply stepping onto a planet's surface could shatter it on arrival. Your heart, also a muscle, would shrink and weaken because it no longer has to push blood against the force of gravity. Eye pressure shifts would physically deform the eyeball, potentially causing permanent vision damage with no corrective option. Artificial gravity through a spinning habitat is theoretically possible, but the engineering requirements make it essentially impossible. Large enough for decades of habitation, sturdy enough to survive interstellar speeds, light enough to actually accelerate, no one is close. The human body was shaped by millions of years of evolution on one single planet. Take it away from that, and it falls apart. And then there is the dimension people always overlook: the psychological reality of total isolation for decades. At the speed of light, a signal from Proxima Centauri takes 4.24 years to reach Earth. A question and its answer: over 8 years. No video calls home, no news from mission control, no updates, no human connection outside the ship for decades. Isolation studies on Earth, volunteers sealed in simulated spacecraft for months, consistently show psychological deterioration, depression, anxiety, cognitive impairment, interpersonal conflict.
And those volunteers knew they could leave at any time. On a real interstellar mission, there is no exit, no abort, no rescue. Just a sealed metal tube hurtling through emptiness. What about generation ships? Entire communities whose distant descendants would eventually arrive. This raises even harder questions. How do you keep a society stable and mission-focused for centuries when the original crew members are long dead? Languages change beyond recognition within a few hundred years. Religions split, governments collapse, cultures drift entirely. History shows us repeatedly that human societies fracture and transform over far shorter timescales than an interstellar voyage. The idea that a sealed community could hold together for a millennium focused on a single objective contradicts human nature itself. And every generation born on that ship never chose the mission. They inherited it.
That changes everything about social cohesion. There is one more danger most people never even consider. Space looks empty. At high speed, it is anything but empty. At 10 to 20% of light speed, a particle the size of a grain of sand would hit with the energy of a hand grenade. A pebble-sized object would strike with the force of a bomb. And there are countless such objects in interstellar space. At those velocities, the spacecraft would be outrunning its own ability to detect what is ahead. No time to maneuver at all. Every second of a decades-long journey would be a roll of the dice against invisible, unavoidable, potentially lethal debris. The probability of surviving that exposure over a journey measured in human lifetimes is not something that works in our favor. So where does all of this leave us? The honest, uncomfortable answer is this. We will not reach Proxima Centauri. Not with chemical rockets, not with ion drives, not with nuclear engines, not with anything we can currently build. The distance is too vast. The energy demands are too extreme. The speed limit is non-negotiable. Physics does not compromise. And even if we somehow solved propulsion, radiation, structural integrity, and fuel simultaneously, the human body would still fail. Some people point to wormholes or warp drives as potential workarounds.
Theoretical physics does technically allow for the possibility, but allows for the possibility and is actually achievable are separated by a gulf as wide as the one between us and Proxima. Wormholes, if they exist at all, would require exotic matter with negative energy density, something never observed anywhere in nature. Warp drives, as proposed by physicist Miguel Alcubierre, would require energy equivalent to converting the entire mass of Jupiter into fuel. These are not technologies approaching development. They are mathematical concepts, beautiful on paper, unreachable in practice. At least with anything resembling our current understanding of physics. The door is not locked. It may simply not exist. But here is what we genuinely can do. We can look, we can listen, and we can aim the most powerful telescopes ever built at distant worlds. Instruments like the James Webb Space Telescope analyze starlight filtering through alien atmospheres light years away. We can search for biosignatures, chemical fingerprints that might hint at the presence of life on worlds we will never set foot on. We can map entire worlds we will never walk on. We can study the physics of places we will never escape to reach. There is a strange and profound kind of beauty in that.
Our understanding of the cosmos reaches far beyond our physical ability to travel it. We are a species that can intellectually grasp the universe while being physically unable to explore even the nearest corner of it. Our intellect reaches infinitely farther than our rockets ever will. And maybe that is not a failure. Maybe that is remarkable. The stars will wait. They have been waiting for billions of years before we ever arrived on this pale blue dot. And even if we never crossed that canyon, the fact that we stood at the edge and understood how wide it was, that matters. Understanding is its own form of reaching. No other species we know of has ever looked up and truly comprehended what they were seeing. Thank you for watching. If this gave you something to think about, a like or subscribe helps more than you know. See you next time.